Okay, here's another cool force problem. In this problem, we have two blocks A and B that are stacked on top of one another. Block A is also attached to this cord that's running over a pulley and attached to block C. The tabletop's horizontal, and let's look at what our givens are here. We're given the mass of block A, so that's something that's known. Mass of block B is known. The coefficient of kinetic friction, and that would be at the interface between block A and the table. So that's where mu sub k is relevant. And the coefficient of static friction, and that is relevant for the interface between the blocks there. That's where mu sub s is describing what's going on physically. So what we're asked to determine is the greatest mass block C can have such that blocks A and B still slide together when the system is released from rest. So kind of first play this movie in your mind a little bit. You can imagine putting larger and larger masses there at C and eventually the two blocks coming apart. But, you can imagine also that there's some kind of range for C where they would start in motion and there's enough static friction between the blocks at the interface between A and B that the two blocks would accelerate together. Yeah. So we know they're accelerating because we're told that the system is released from rest. And if it doesn't stay at rest, then it's accelerating because the velocity is changing. So let's go ahead and get started on this one. Um, Again, as always, you want to go ahead and start with your free body diagrams. Our pertinent equations here are going to be Newton's second law, super important, and then force of kinetic friction is equal to mu sub k times the normal force, force of static friction less than or equal to mu sub s times the normal force. You'll notice that I always use that inequality that's in the definition of static friction. And remember, that's because static friction is the one whose magnitude can vary, right? It can depend on what's going on in your particular scenario. So if that's still feeling kind of strange to you, I would say go back and review that. In these problems, this is why I ask for a lot of like what is the greatest mass block C can have, right? So what I'm wanting that maximum. I'm wanting the it to be necessary to apply the maximum amount of static friction. So if this is true that static friction is less than or equal to mu sn, what that means is that the maximum force of static friction is equal to mu s times n, right? That's the maximum value it can have. Okay. So again, static is there's more subtlety to static friction than there is to kinetic friction. So I like to make sure that we work with it. So free body diagrams, go ahead and get started on those. We need three, block A, block B, and block C. So you can consider the forces that are going to appear on your free body diagram here. Let's start with block C. Again, that'll be the simplest one. What do we have going on for block C? We've got the weight of block C downward, and then we have tension upward. I can just call that T. There's only one length of cord here. There aren't two. There's only one, so I can say the tension in that cord I'm going to call T. I don't need anything else as far as notation goes here. For our coordinate system and for sign convention here, what I want to do is positive in the direction of acceleration. So for block C, it would be accelerating downward, and I'll say then positive downward for that free body diagram. All right, I'm going to go to block B, which is probably the next simplest one. I have the weight of block B. And then what is in contact with block B? The only thing it's in contact with is the top of block A. So the surface top of block A is touching block B, and that is providing an upward normal force. I'll just call that N sub AB. That's the normal force at the interface between blocks A and B. And then Think about it. At that interface, there's also a frictional force. In fact, it's a static frictional force. And block B is accelerating to the right. So that force must be accelerating to the right. It's the force that's responsible for accelerating block B to the right. There are no other forces on the x-axis for block B. Positive in the direction of acceleration here, and then for my y-axis, it doesn't matter. I can say positive up or down there. We don't have acceleration in that dimension for block B. For block A, now I can start looking at A. I know I've got, what do I have downward? I know I have the weight of block A downward, and block A is also attached to the cord, right? Block B is not. The cord is not touching block B. So that does not belong on the free body diagram for block B, but it does for block A. So it's in contact with A. That would be a rightward force on block A. We're calling that T there. And then what else is in contact with block A? Well, the surface beneath it is in contact with it, and that's providing a normal force that's straight up. I'm going to call that N sub A. I'm not analyzing the surface beneath it, so a single subscript works there for my meaning. And the block A is sliding to the right. So to the left, I know I've got my force of kinetic friction. And then I also have to the left my force of static friction. And this throws a lot of students, that force of static friction right there. And I want to pause for a moment. I know we're not done with this free body diagram, but I'm going to pause and treat this. So there are a couple things that might work for you. One is if you're pretty solid on Newton's third law, you would know that the static force that is static frictional force depicted on the free body diagram for block A, that is makes a pair with the static frictional force that is depicted on the free body diagram for block B. So those are part of a third law pair. They must point in opposite directions. It might be more obvious to you when you look at block B that that force of static friction must be directed rightward because, as I've said, logically, it is the only force that's responsible for the rightward acceleration of B. There is simply nothing else in contact with B, and we cannot include magical forces in our physics. So we that helps us reason out that the force of static friction is rightward on block B. That logic can help you understand why it must be leftward on block A if you consider that they are part of a third law force pair. You can also, if thinking about static friction is just a little bit too abstract for you, you can consider the interface between block A and B as being somehow hooked together. So, like, allow there to be some kind of hook here. Let this be block B, and then down here, let's say the interface of block A or something, um, and have them be like connected in some way here. So if it helps you to think about it that way, or actually maybe I should draw it instead of directionally. Sorry, bear with me. I want to try to make this a little bit more physical. I know physical always helps me. So consider there to be like a notch in block A, and then just kind of like tongue and groove in carpentry, right? That from block B fits into that notch. So this is block B. This down here is block A. Okay. And this is like a super exaggerated way of thinking about friction. So let me just hatch on block B here so you can see that they're separate blocks. Now you can see that if I take block A and I pull block A to the right through that tension force, block B is going to come with it. So again, this is like a overly simplified, exaggerated way of thinking of frictional force, but what it can do is it can help you see that when that happens, that frictional force, or what is the dynamic that would be happening inside this notch, would be basically pushing B to the right? That acceleration to the right. And as that happens, block B would be in turn exerting an equal and opposite force on block A. So what block A is feeling is a force to the left, what block A is experiencing. I'm going to just do one more analogy on this because I know how hard this can be for students. One of the reasons this is hard to understand is like, say I'm pushing a piece of furniture across the room or something. What my brain focuses on in that case is me pushing it and the force I'm exerting on it to push it across the room. What my brain doesn't focus on, but what exists, what's just as real, is that the piece of furniture is pushing back on me exactly the same amount. So if I am going to exert 20 newtons of force on that piece of furniture, guess what? It's exerting 20 units of force or 20 newtons of force backwards on me. But our brains don't think in an everyday way of that force that's coming back, right? The opposite force. So that might be why, if you're really feeling like it's not intuitive, it's not you. It's that it isn't as intuitive. It's not something that we analyze. We can go about our day and never think about it, and it doesn't really get in our way. But we have to think about it when it comes to solving these problems properly. Okay. Hopefully, you know that we're not done with the free body diagram for A. We haven't considered everything that's touching it. So I want to just go back for a second. So we got our one invisible force on block A, which is weight. The strings touching it, we've got tension. The surface beneath block A is exerting a kinetic frictional force and an upward normal force. But there's also contact, and we were just getting into that at the top of block A, where it's in contact with block B. That interface exerts frictional force, which we have to the left, our static frictional force, but it also exerts a normal force downward. That's NAB. And that is part of another um, pair. Here we go, another third law pair right there. So you can see these two blocks, right? That forces are interactive. Forces don't occur in isolation. Every force in the universe is an interaction. I'm going to say that again. Every force in the universe is an interaction. Okay. Cool. Let me put a sign convention on this. Block A is will be accelerating to the right, so I'm going to call that rightward positive. And with our free body diagrams complete, we're now ready to apply Newton's second law and render some equations here. So I'll start with free body diagram A, and I'll start with the x-axis as I usually do. So tension minus F sub k minus F sub s equals mass of A times its acceleration. And then I'm going to go ahead and write out the y equation while I'm still focused on this free body diagram this time. N sub A minus the weight of A. Oh, actually, I'm going to go ahead and pop in the magnitude of A right now because we're given M sub A times G minus the normal force AB is equal to 0. I don't have any acceleration along the y-axis. Okay, for block B, a little simpler. Force of static friction equals mass of B times its acceleration. Again, these guys are moving together, so I can use the same acceleration. Pretty nice there. Then I can look at my y as well. Normal force AB is equal to, I'm sorry, minus, weight of B, but I'm going to write that in, I'm going to put its magnitude in right now. Mass of B times G equal to 0. And then finally from C, nice and simple, weight of C, did it again, mass of C. Oh, that's what we want to find, right? Minus tension is equal to mass of C times acceleration. You have to be careful here, and you don't want to on autopilot where you're telling yourself, oh, whenever it's, the up and down, the acceleration is always 0. That's not always the case. So just every free body diagram is its own thing. Be sure that your brain is turned on and that you are really looking at every case, and um, try not to be on autopilot. I think for really any part of these problems where you're engaged in the physics, that can get you into trouble. So I think that's most of our physics is done at this time here. And I'm going to flesh out really quick the frictional forces, and then I think we're ready to go. So the force of kinetic friction here, that's going to be equal to the coefficient, which is given, multiplied by the normal force. And which normal force is that? Look for it. Force of kinetic friction acts at the interface between block A and the table. So the normal force for that interface is N sub A. The static frictional force is equal to the static frictional coefficient, which is given, multiplied by the normal force that acts. Now, this is different interface, right? We're talking about static friction at the interface between the blocks. So now we're looking at the normal force that occurs at the interface between the blocks. That is N sub A B. So we need to have those definitions, and basically those definitions are going to be used as we apply the other equations together algebraically to come to our solution here. And what we're being asked here is to solve for is the mass of block C. So just keep your eye on the ball and use your favorite algebraic technique. As always, all the algebraic steps can be found in the written solutions.